Our next question is from GATE 2019, mass transfer for 2 marks. A countercurrent absorption tower is designed to remove 95% of the component A from an incoming binary gas mixture using pure solvent B. The mole ratio of A in the inlet gas we have given, carrier gas flow rate we have given, the equilibrium relationship we have given, where y and x are the mole ratio of the A in the gas and liquid phases respectively. If the tower is operated at twice the minimum of solvent flow rate, mole ratio of A in the exit liquid stream is. Let's start with the solution. You can see here y1 we have given, gas stream we are calculating, we are considering with y. So y1 is equal to 0.02, the mole ratio entering, and it is given that we are removing 95%. If we are removing 95%, then it will be 1 minus 0.95 into 0.02 y2. It is a exit stream concentration, or you can say mole ratio in the exit stream, that is 0.001. We know that the gas flow rate, it is a carrier gas, gs is equal to 50 kilomole per hour. Next, you can see here this is the equilibrium line, y is equal to 2x we have given, y is equal to x, right? And it is a operating line. Since we have you can see here this is a packed tower, right? Y1 is entering, y2 is exiting, that is mole ratio, right? X2 is the mole ratio of the solute in liquid phase, x2 is entering and x1 is exiting. So you can see here x2 is 0, right? X2 will be 0 since we are using pure solvent, and x1 will be something, there is something value, x1 will be non-zero, and y1 is entering, y2 will be less, right? So you can see here y2 will be less, so we will point it out, write this y2 and x2, and y1 will be higher, so we can say y1 is this, and x2 there is something, x1 is something here. But whenever we calculate the minimum solvent flow rate, then we need to touch this line at equilibrium. It will touch the equilibrium line. At this point, we get the minimum solvent flow rate. How? Since the slope of the operating line is given as ls by gs, right? And if we decrease the value of ls and gs is fixed, then this is continuously decreases, and we will just we cannot cross this equilibrium line, right? We just touch this equilibrium line. So let's say this green line is showing that minimum solvent flow rate, right? From here we are getting x1. So you can see here, so we will apply the material balance. You can see here ls into x1 minus x2 and gs is equal to y1 minus y2. You know that y1 is higher and y2 is lower, right? So and since we are calculating it at equilibrium, so we will calculate the value of x1. You can see here we are calculating the value of x1 at equilibrium. Since it is this line is cutting, this line is cut at the point of x1 comma y1, so we will put the value of y1, then we will calculate the value of x1 from the equilibrium line equation. Since it is given that y is equal to 2x, so x1 is equal to y1 by 2, it will be 0.01. so from this I will put the values, ls into 0.01 minus 0 into this. From this I got ls minimum, that is 95 kg per hour, and it is given in the question that we have given in the question that if the tower is operated at twice the minimum solvent flow rate, right, the mole ratio of A in the exit liquid stream is. You can see here, if I increase the ls means solvent flow rate, then it will shift to here. This is the black line, right? So you can see here LS optimum will be 2 into LS minimum, that is 2 into 95 kg per hour, that is equal to 190 kg per hour. Now I will use this is LS to calculate the value of X1. So again we will use the material balance LS into X1 minus X2 GS. Since we are not changing the GS, Y1 minus Y2, we know that we are decreasing it, we are extracting 95% of this solute. So you can see here from this we get X1 is equal to 0.005. This is the final answer. So thank you. Please make sure to like, share and subscribe my channel. Thank you.